Good afternoon. My name is Brian Hastings. I'm a geologist with a small employee-owned consulting firm based out of California, specifically in Truckee. I've been with the company for 22 years. I'm a professionally registered geologist with a background in fluvial geomorphology, restoration, and water quality. My talk today is about nitrogen source tracking in a semi-arid watershed using stable isotopes. I'll walk you through some of the background and setting of my project, the study design approach that I chose, and walk you through some results as well as conclusions in the next 15 minutes. At this time, the project location is confidential, therefore I will refrain from using place names. So all the maps that you'll see in this presentation will be simplistic, but at least convey the information that you need to understand what the project was about. You can know that the project was located in the Basin and Range geomorphic province. It's a semi-arid area, roughly 13 inches of rainfall or precipitation a year. And it was originally a closed basin. A closed basin, like all watersheds in the Basin and Range, have no outlet. Runoff is collected into a playa and infiltrated or evaporated. However, in 1870, an irrigation ditch was constructed in this project basin to import river water from a nearby river, which is mostly derived from snowmelt runoff. Um, the ditch imports water into the basin, typically during irrigation season, between April and October of each year. The ditch has been unlined since its construction, so it does contribute to groundwater recharge just by ditch leakage. To avoid flooding the basin being previously closed, a drain had to be constructed to export waters out of the basin. The drain is now the only perennial feature in the basin. Total nitrogen concentration measured at a station over a 12-year period from base flow and stormwater are shown here in the graph. They provided a wide range in values, anywhere between 1.3 to 6.3 milligrams per liter, which may be attributed to the diversity of nitrogen sources. What's interesting or important to note here is 100% of the samples collected over this long period exceeded the locally established water quality standard for total nitrogen, 1.2 milligrams per liter. And that is in contrast to the total nitrogen concentrations in water imported to the basin via the irrigation ditch, which all have measured less than 0.25 milligrams per liter, or the reporting limit for that constituent. Total nitrogen concentrations were correlated with measurements of stream flow measured instantaneously when samples were collected, but the results did not show any trend of increasing total nitrogen with increasing stream flow. Highest concentrations were measured in both low and moderate flows. In this plot, we examined total nitrogen concentrations collected from automated samplers over a 6-year period. Samplers were collected using automated samplers using time pacing methods to capture multiple samples in a single storm event and across multiple events to identify if there was any interstorm variability. Base flow was also sampled using automated samplers and collected samples on an hourly basis and composited into 6-hour periods over a 24-hour time. We then applied a Mann-Kendall statistical test to evaluate presence, strength, and significance of any trend that we detect. We found a significant, moderate, and increasing trend in these data, essentially showing that nitrogen was increasing over time. But what were the sources of nitrogen? Where were they originating from? Land uses are complex in the basin, in both space and time. Historically, the basin was used for open range, agriculture, hard rock mining, and in time, rural residential began to increase and replace some of those uses. A lot of the rural residential were on septic systems, not sewer. And more recently, there's been a rapid urbanization over the last decade or two, with mass grading for housing and commercial, including golf courses and associated landscaping. Today, less than 1% of the basin is still irrigated for ranching. A study design was needed to address the complexities in land use and other spatial and temporal variables. So I designed the study to look at some of these different variables. Spatially, we bracketed different land uses, collecting samples upstream and downstream of known different land sources like urban or agriculture. We also collected samples with distance downstream to see if there were changes as water was exported out of the basin. And we also looked at differences between surface water and groundwater using both shallow and deep wells, as well as at a stream gauge. On a temporal scale, we looked at different water quality in stormwater and base flow. We looked at low flows and high flows, and then also collected samples during the irrigation season, April through October, and the non-irrigation, October through May. We collected and analyzed samples for major ions, common physiochemical values, nutrients, and specific stable isotopes of nitrate and boron, those being O18 of nitrate, N15 of nitrate, and boron 11. We also complemented these samples and these analysis with other selected environmental tracers, including chloride, emboss, oil, and grease. For the purposes of this talk, I'm mostly going to focus on the stable isotope results and also show you a little bit of background or selected environmental tracers as a secondary line of evidence. The sampling locations for surface and groundwater are shown in the basin with an aerial overlay on this map. 3 locations were chosen to characterize background samples, identified here as BGS. Those are samples or locations upstream from urbanization and representing undisturbed or open space within the basin. Samples were also collected from imported waters from the irrigation ditch that came in, imported waters from the river, the drainage channel that exported waters from the basin, and again, shallow and deep groundwater. Hydrologic conditions during the study period are shown here using a hydrograph from the drain discharging the basin, a USGS gauge. The drain is perennial. Daily mean stream flow ranged between 0.7 CFS up to 75 CFS. Yellow dots indicate when samples were collected for both concentrations of nutrients and isotopes. Samples characterized base flow in stormwater and across both non-irrigation and irrigation seasons, as shown by the graph. These 4 maps show total nitrogen concentration in base flow in groundwater across different times of the year. The increasing concentrations are shown here as increasing in size of the circles and change in color. Green representing it meets local or regional water quality standards, whereas red shows some of the highest values measured. Under periods when no river water was imported to the basin, shown here in the top 2 graphs or maps, the total nitrogen concentration increased in the downstream direction. As we look at the 2 lower maps during the irrigation season, total nitrogen concentrations in imported waters were low or non-detect, but generally showed increasing concentrations when discharged from the basin. Also noted here, total nitrogen in groundwater measured at the same time indicated some of the highest concentrations we measured, suggesting total nitrogen could be sourced from septic contaminated groundwater. The 2 maps I'm showing here show total nitrogen concentrations during a winter and summer storm. Not all locations could be sampled during some storm events, given the nature of these storms. But non-urban background samples showed elevated concentrations of total nitrogen, shown here in the red, in larger circles. And that, of course, is in contrast to the surface waters draining the basin. However, total nitrogen increases were still measured in the downstream direction of the drain. Now let's look at some of the isotopes that we collected for these samples. Shown here is the dual isotope approach, comparing O18 of nitrate to N15 of nitrate. All the different dots on there are my sampling points and their isotopic values in per mil. The different colored boxes represent N members, from both local, regional, and what's been identified in the literature for different sources. Using these two isotopes is complicated and problematic. And in this case, there was many sources that overlap in the isotopic range of values. Second, nitrate is subject to fractionation, in this case denitrification, and that can change your values over time or in downstream directions. So the addition of boron isotopes, or boron 11, helps tease out some of these sources. What you see here now is those N members are separated when we compare the boron 11 values to the N15 isotope values of nitrate. And 17 of the 35 samples that I collected were identified as manure-related sources, both in surface water and some in shallow groundwater. However, there remains some overlap in distinguishing fertilizer from septic sources, as shown by the graph, but a well-designed study can help interpretation of overlapping results, shown here. For example, two data points out there identified as the green triangles represent samples collected from stormwater runoff from known fertilized landscaping. So we believe those samples are representing the fertilizer using those isotopic values. We also have used other local studies to help define these N members, including known contaminated wells of septic and nitrate. Still, results suggest manure may be the primary source here, but multiple sources can and do still exist. I want to pause here just to share something with you now that I've shown you some of the isotope data. From Kendall and McDonald's book, 1998, Isotope Tracers and Catchment Hydrology, I found this quote quite interesting, and it's known as Fretwell's Law. It says, "Warning, stable isotope data may cause severe and contagious stomach upset if taken alone. To prevent upsetting reviewers' stomachs and your own, take stable isotope data with a healthy dose of other hydrologic, geologic, and geochemical information." And that's to be Pardon me, and that's to say that we should be looking at some of the other lines of evidence used in this study. One of them that I want to bring your attention is sodium chloride ratios. There are potential influences from known septic contaminated groundwater, which can be inferred from these ratios. A 1-to-1 ratio, for instance, of low concentrations would indicate fresh water. So from the graph on your screen, you see some of the background sites and in the irrigation ditch. The water is being brought in from the nearby river, mostly plot on low concentrations and mostly close to a 1-to-1 ratio, slightly higher with sodium enriched. But the samples with excess chloride relative to sodium, a ratio less than 1, would suggest septic contamination. Those might be these two green dots here representing shallow groundwater in wells that were known to be close to septic systems. In contrast, all of the surface water samples collected as part of the study do indicate a ratio greater than 1, shown here in all of the open circles. Yes, high concentrations of sodium and chloride, but they're sodium enriched, which can occur from urban and/or agricultural runoff, including manure-enriched soils. In the absence of cattle ranching, agricultural land uses, impacts from disturbances of legacy land uses may be the sources of manure and nitrogen pollution. So if the main sources of nitrogen pollution in this basin is manure, where are the cattle? A likely explanation may be the conversion of historical ag grazing lands to urban uses. Shown here is a comparison between a 1974 aerial on the left and a 2022 aerial on the right. Both of these are zoomed into the center of the basin, where you can see a lot of the new development has occurred in which was previously irrigated ranching lands. A 2003 review of soils with historical applications of manure and cattle ranching found that soils continue to be enriched in nutrients years after their application, even years after those land uses were terminated. New development in the basin includes mass grading and disturbance of these formerly agricultural lands, and if construction best management practices are limited or absent, these disturbances can increase erosion and transport of nitrogen-rich soils to the drain. Here's what we can conclude from this study. The use of boron 11 has increased our ability to identify the nitrogen sources in the basin, including teasing out and differentiating between those from septic and those from manure. N15 and B11 results suggest the main source in this case of nitrogen pollution in surface waters may be originating from manure, including cattle directly or manure-applied fertilizer. However, current cattle operations within the basin occupy just less than 1% of the basin today. So where is the manure coming from? Well, based on our analysis of the study design and the location, we believe that mass grading for urbanization purposes is disturbing soils that are rich in nitrogen from these historic land uses. And maybe the lack of or limited use of construction best management practices during this urbanization period is likely mobilizing manure-related nitrogen in those disturbed soils. However, results may also indicate there are different sources, and they could be mixed, not just manure. And they may include septic, fertilizers, and/or atmospheric deposition. That's why we heavily emphasize that the use of environmental tracers or other supporting evidence can help support and help to identify the different mix sources. Thank you very much.